Good morning, everyone. So in today's video, I'll be talking about the Lamport's mutual exclusion algorithm. So what is Lamport's mutual exclusion algorithm? Lamport's distributed mutual exclusion algorithm is a permission-based algorithm proposed by Lamport as an illustration of his synchronization scheme for distributed systems. In permission-based timestamp is used to order critical section requests and to resolve any conflict between requests. In Lamport's algorithm, critical section requests are executed in the increasing order of timestamp. A request with smaller timestamp will be given permission to execute critical section first than a request with larger timestamp. So, there are three types of messages. There are request, reply, and release. So it is used and communication channels are assumed to follow first in and first out order. So a site send a request message to all other sites to get their permission to enter critical section. A site send a reply message to requesting site to give its permission to enter the critical section. Then a site send a release message to all other sites upon exiting the critical section. So next, the algorithm. So enter critical section. When a site S wants to enter the critical section, it sends a request message request timestamp I to all other sites and places the request on request queue. Here, timestamp denotes the timestamp of site S. When a site S receives the request message request timestamp I from site S, it returns a timestamp reply message to site S and places the request of site S on request queue. So to execute the critical section, a site S can enter the critical section if it has received the message with timestamp larger than timestamp I from all other sites, and its own request is at the top of request queue. And to release the critical section, when a site S exits the critical section, it removes its own request from the top of its request queue and sends the timestamp release message to all other sites. And when a site S receives a timestamp release message from site S, it removes the request of S from its request queue. So, message complexity. The Lamport's algorithm requires invocation of 3n-1 messages per critical section execution. This 3n-1 message involves n-1 request messages, n-1 reply messages, and n-1 release messages. So the drawbacks of Lamport's algorithm. So a reliable approach, failure of any of the processes will halt the progress of entire system. High message complexity, algorithm requires 3n-1 messages per critical section invocation. So the last one is the performance. Synchronization delay is equal to maximum message transmission time. It requires 3n-1 messages per CS execution. So the algorithm can be optimized to 2n-1 messages by omitting the reply message in some situations. So now from this, S1, S2, and S3, you will see the messages passed on all the other processes. From S1 goes to S2. From S2, it goes to S3. From S1, it goes to S3. From S2, it goes to S1. Here, the messages 2, 1, the critical state, that is means, and it is asked for our resources. S2 receive 1 and 2. As these are the two thing value where the message needs to be passed, it has requested it again, has the requested execution, and the release of the critical state. 3-step, all the algorithms follow as first is requesting of the critical state, and then executing in the critical state, and then releasing from the critical state so that the resources can be used by other processes. As S2 has asked for the first time, the timestamp of S2 is 4, so S2 will enter the critical state first over here. Now this what is there 1 and 2, but 2 has the first timestamp, so it will enter the critical state first over here. And same thing, is it there for the first ones? It enters the message pass on the S2, and this is where it shows that S2 has entered the critical state with the permission from the S1 and S3. Once S2 is entered at the critical state, then what happens is it releases now, and it releases all the resources which were there And now when these resources are released, then what happened is the S1 will enter the critical state. And the message is passed that it's releasing, so now S2 exits the critical states. Then after that, S1 will enter the critical state over here. And this is how it proves that S1 can enter the critical state only after S2 releases it. Thank you.